Now that we have some experience in writing expressions for the motion of a projectile, let's use that to find some quantities, some numbers here. So one problem that I've seen a lot on these old AP tests and other places is a situation where we're throwing something from the top of a tall building or a cliff or something like that, and we're wondering how far it's going to land from the base of that cliff. So I've set up a problem like that here. We've got some initial velocity of 15 meters per second, 20 degrees above horizontal. We start up here at a height of 22 meters above wherever the base of the cliff is, or street level if this is a building. The question is, how far away horizontally is this going to land? So with all these problems, it's a great idea to start by just identifying what it is we know and what it is we're trying to solve for in terms of the variables in the kinematics equations. So we can break everything down into x stuff and y stuff. So we would be interested in the initial position and the final position and the initial velocity and the final velocity and the acceleration and the amount of time that goes by for any part of the path. Go. You can always fill in accelerations on these. For projectiles, it's always 0 for the x, negative 9.8 meters per second squared for the y. Now let's see what else we can do here. I've got this 22 meters. That's a vertical distance, so that'd be my initial vertical position, my initial y position. And I know it's going to end at street level, or the base of the cliff, at a height of 0 meters, or just 0. We don't really need units if it's a 0 there. Let's see, initial x position. There's really nothing given to us here. We might as well just call that 0. So right here is 0, and then we're looking for how far it travels horizontally, so we want to know, where in the x direction it lands. So our ultimate goal then is to get to x final. What is that value? Okay, and then we have also this 15 meters per second at 20 degrees above horizontal. Now, I can't put that into x or y because it's got components in both directions. So let's figure out what those components are. This is our vector resolution stuff we worked on a few videos ago. Alright, so we got 15 meters per second at 20 degrees. Okay, so this will be v naught x, and this will be v naught y, and a right angle there. And so v naught x is going to be the 15 meters per second times the cosine of 20 degrees, and v naught y is going to be the 15 meters per second times the sine of 20 degrees, and so the 15 and 20 degrees. Okay, good. So 15 times the cosine of 20 and 15 times the sine of 20. So we get 14.1 meters per second and 5.13 meters per second here, so we can fill those in. 14.1 meters per second and 5.13. Okay, so now this chart represents a complete picture of everything that we're given at the beginning of this problem, and we know that we're trying to get to this x position at the very end. So there's a couple of ways that we could approach this. Sometimes if you're stuck on where to go with these problems, it's useful to just pick out an equation that has the variable that you want to get to at the very end in it. And that might help you to see what the what the next few steps are. Right now we also might just be able to solve for x directly. So let's take a look at that. I'm going to clear a little more space down here. Get rid of this. We don't need that anymore. There we go. Okay. So in the x direction, let's see, if I'm looking for the final x position, I've got, let's see, x is equal to x naught plus v naught t plus 1/2 a, that's in the x direction, times t squared, that x direction as well. So looking back at the information that I have here, we've got x would be equal to 0 plus 14.1 meters per second times t, I don't have that yet, so we'll just leave it as a variable, plus 1/2 times 0, so it'll just be 0 here. Okay, so my x position then is going to be 14.1 times t, and t is, well, I don't know it yet. Okay, so from this equation then I understand, first step we got to figure out what t is. And I can do that on the y side of things. So if you play around with the other equations on the x, you'll just find that we don't have enough information to find out what the value for t is there. You might try something really clever, really tricky, and use this equation, vx equals v naught x plus acceleration in the x times time, and then, well, we can do this one because we know the final velocity in the x would just be the same here, 14 meters per second, because it's not accelerating. So now we know the starting velocity and the ending velocity and the acceleration, and whoa, jumping around there. So the only thing I don't know there is time, so I can plug in 14.1 meters per second is equal to 14.1 meters per second plus 0 times t is 0, and I've just successfully proved that 14.1 is equal to 14.1. And that's great. Not a really useful answer for me, but it's true, I guess. Okay, well, anyway, let's come back to this x direction business once we've figured out time in the y direction. Okay, so in the y direction, let's try this equation again. Y is equal to y naught plus 1/2 times v naught y. Whoops, making up equations here. Don't make up your own equations. Newton did a nice job for us. V naught y times t plus 1/2 ay times t squared. Don't need to reinvent the wheel here, just use the equations we're given. Okay, so our y position then is going to be 0 is equal to 22 meters plus v naught y is 5.13 meters per second times time plus 1/2 negative 9.8 meters per second squared times t squared. So I can simplify this a little bit. 0 is equal to, I'm just going to cheat a little bit here and not write down the units because I think that just makes it a little more complicated. I'm going to write this in order of squared term, then linear term, then constant terms, just so this looks familiar to you. So this is negative 4.9 t squared plus 5.13 t plus 22. Okay, so this is a quadratic equation. We can solve it by graphing it. We can solve it using the quadratic formula, maybe by factoring, maybe by voodoo. Okay, maybe not by voodoo. That's probably not the specialty of voodoo, is solving quadratic equations. So maybe we ought to use one of the other methods here. The other alternative here is, if you really are uncomfortable with these quadratic expressions, well, number one, get comfortable with them because we're going to use them. But number two, you can get around that if you want to. I mean, we've got, let's see, everything on the y side here except for the final velocity in the y. You could solve for that as your first step and then use that to get the time, and then use time to get this position, the final position. Or, since we don't need the final velocity in the y, we can just Well, let's suck it up and let's deal with this this expression. Okay, so your calculator might even have a built-in solver on this, so check into that. That's a really easy way to solve these ones. I'm going to go old school on this, though. I'm going to solve this using the quadratic formula. And as my good friend, the math teacher, Sam Hunter, would tell us, we're not going to use x, we're going to use t here, but t equals negative b plus or minus square root b squared minus 4ac all over 2a. Ha! That's how he teaches his students, or how his students help to remember it themselves, I guess. So he's the math teacher. I'll defer to his wisdom. So the b is the second coefficient, the a is the first coefficient, c is the third coefficient, so we can just plug in here. T is equal to negative 5.13 plus or minus the square root of 5.13 squared minus 4 times 4.9 times 22 all over 2a. 4.9. Okay, so then t, when we solve this out, one of the roots that we get is going to be probably some negative number, and that corresponds to, if this parabola were to continue backward like this, how far back in time we would have to go to get to where it was at a y position of 0 again. But we're not traveling back in time, and even if we did, this projectile, this rock or whatever, it wouldn't be traveling through the building like this. So we're only going to use the positive root for this situation. They'll have two roots, but you should be able to tell which one is the one to use. Okay, and I can't forget my negative sign there, that's important. So let me type this in, negative 5.13 plus the square root of 5.13 squared minus 4 times, oops, I forgot a negative sign there too, times negative 4.9 times 22, and then that whole thing is over negative 9.8, and I get a mistake. Oh, there it is. Got to be careful on these ones. There's so many little places to go wrong. I typed in 513 instead of 5.13. That will throw you off. Okay, divide that by negative 9.8. And it still seems a little high. Let me double check my math. Let's see, 4 times 4.9 times 22, square root then, whole thing. And oh dear, I only divided the second term by that 9.8. That's a goofy thing to do. Let's see. Negative 5.13 plus, let's see, I have some weird factor of 50 in here. My goodness, no wonder I usually avoid this process. Okay, and it looks like we need to do the negative one on this one. So minus, alright, and divided by negative 9.8. Alright, wow, that takes a little while, but time is 2.7 seconds. There we go. Okay. So, definitely, if you've got that solver built into your calculator, if you know how to solve this by graphing, that's the way I would go. This quadratic formula, yuck. So, that's 2.7 seconds. Alright, and we're out of space again, so let's clear a little more. Goodbye, quadratic formula. Get out of here. Okay, so we can go back to that equation we had written a minute ago. X equals x naught plus v naught xt plus 1/2 ax times t squared. X is going to be equal to 0 plus 14.1 meters per second times 2.7 seconds plus 1/2 times the 0 times t squared will just be 0. So then x is going to be equal to 14.1 times that 2.7, and we get 38 meters. 38 meters away is where that thing's going to land. So general process on this, though, use a table like this to set up your given information. It's unbelievably helpful, and just having everything separated into y stuff and x stuff is so important because we can't mix and match. I can't put a 14.1 meters per second with a negative 9.8 meters per second squared because one's on the x side and one's on the y, and we're treating these two separately. So use some system anyway to organize your work, but the table is a good way to do it. If you're not given a picture, draw a picture. You can kind of sketch this out, like roughly to scale, and get a general idea of how your answer makes any kind of sense. And so here I have a rough picture of what this thing would do, and we got 22 meters there, and it looks like a little further than 22 meters. And I'm just guessing on the sketches, but I got an answer that was a little more than 22 meters, about double that here. And if I'd gotten a number of like 800 million meters, I would have known that was wrong, or 0.5 meters, I would have gotten that was wrong too, just from the sketch. So take that little extra time, organize your work nicely, make a sketch so you can see the picture, and then we just kind of see what we can do with the information we have. Try and fill in this table until you get to the answer that you're looking for.